Well, dear students, so hopefully this is the last topic of ionic bonding. Although this topic involves some thermodynamic parameters, but I will try to explain you here this lattice enthalpy, because this enthalpy word itself, it is a thermodynamic word, and energy, it is more familiar for you, but enthalpy, this is purely thermodynamic word. So slowly, you will understand, but I will try to explain here. See, there is one point I have marked, that point, that the solubility. See, in the see ionic bond conducts electricity and soluble in water but insoluble in organic solvent. So this solubility and solubility of ionic compounds we can explain on the basis of this lattice energy and hydration energy. Right? These are two very important point, and you will get this hydration and lattice enthalpy, and particularly hydration energy in organic chemistry also. So let's discuss this lattice energy. So all ionic compounds are exist in a crystalline solid, and I have shown you one lattice for sodium chloride, right? So first we see what is this lattice enthalpy. So lattice enthalpy, suppose that we have a metal ion in gaseous state plus some anion, suppose that mono anion X minus in gaseous state. So when cation and anion both are in gaseous state and they combines with each other to form the lattice of mx solid. So whatsoever energy is changing in this whole process, initially they were kept at infinite distance, m plus gas and x minus gas. There is no energy between them, potential energy between them. So whatsoever the energy changing in this process is called delta H lattice. Delta H lattice, right? So you always get this lattice energy in the negative. Suppose that this is what minus y kilojoules per mole. So first point I would like to differentiate here lattice enthalpy and lattice energy. See, this lattice enthalpy, this will come into the negative, and when we define energy, so we will define the amount of energy required to dissociate. So basically this energy we are defining for the opposite process, means from mx to this. So basically the magnitude is same for lattice enthalpy and lattice energy, but the sign is different. So if you define the same equation from left to right, then this is lattice enthalpy, and if you want to define this from right to left, then it is what lattice energy. So lattice enthalpy, it is defined as lattice enthalpy defined as the net heat change heat change at constant T and P when net heat change in the formation of in the formation of 1 mole of 1 mole of crystal lattice from constituent ions, right? From gaseous state, which are in gaseous state. Gaseous state. But see, this is solid, and you have to consider from gaseous state. This means ion should be in gaseous state, but your crystal which is formed, that should be in solid. So you have to consider from gaseous state whatsoever the steps, means if you are cooling, then in the cooling whatsoever the energy is released, that is also included in this. Okay, so this is the net heat change. This is the net heat change. So lattice enthalpy is defined as this what as a thermodynamic parameter. So that's why we are using here delta H. But you know, lattice energy, this is always reported positive. This is always reported positive. But when lattice enthalpy is given, then you will find, I will show you, I will give you some data table, and that will clearly indicates that this lattice enthalpy for stable crystal, this is always negative, right? See here, free energy of hydration, and these are the lattice energy in kilojoules per mole, lattice enthalpy. All these are lattice enthalpies. So this lattice enthalpy is in for stable crystals, this is always negative. So you can write here for stable crystal, stable crystal delta H lattice is negative, right? Not positive. Okay. Okay. So which type of model we are taking here? We are taking here electrostatic model of the crystal. Which model we are taking here? Electrostatic model. We are taking here electrostatic model. See, this is lattice is based on, this lattice energy calculation is based on the electrostatic model. Electrostatic model. Right? So see, this is a 1 unit cell of sodium chloride lattice, as I have shown earlier. Now if you see, if you have only one Na plus gaseous and Cl minus gaseous, and they are placed at what distance r, then the energy between these two by Coulomb's law, you can write, or we can write this energy is equal to minus Z plus z minus z minus z into z minus into e square by 4 pi epsilon naught into r. So this is the simple expression when only two ions are there and they are treated as a point charge. Only two ions are there and they are treated as a point charge, and the internuclear distance is r between them. So the energy is given by this equation. Force is q1 q2 by r square 4 pi epsilon naught r square. So energy is by r, same as we have already discussed this in Rutherford's model like that. Okay, but if you see this one unit cell, this is not the actual situation. Only one ion is not there. There are so many ions, and in surrounding of these ions, some other ions are also present. There is some repulsion, some attraction. So see, this is not basically asked to you to calculate this, but you should have some elementary idea to answer the theoretical question. Suppose that they have given two different compounds and they ask, okay, tell me which has a higher lattice energy. So at least you should know, but I am giving you the exact formula, and which formula we are basically using for lattice energy. So lattice energy it is represented by U. This is equal to minus Na into Z plus into Z minus into E square. One more constant we are taking here, A, divided by 4 pi epsilon naught r plus B into Z plus into Z, B into Na by r to the power n. This is equation 2. See, all of you are knowing all these terms here, Z plus Z minus, right? Z plus Z minus E, R, Na. Sometimes all of you are not knowing here, so let's discuss A. A is a constant called Medulung constant. Medulung constant. And B is called, and value of this Medulung constant depends on the geometry of the crystal, right? So not required for you people. You just know what is this A. That's it. And B is called the nearest neighbors, basically coordination number. For example, here in sodium chloride crystal, one sodium ion is surrounded by 6 chloride ion, and one chloride ion is surrounded by 6 sodium ions. If you analyze the complete lattice of sodium chloride, so basically B is the number of nearest neighbors, nearest neighbors. Nearest neighbors, right? and this n is constant, small n, this is constant, determined experimentally, and r is the internuclear distance, Na is the Avogadro's constant. Now see, okay, rest things are known. See, what is this Z plus Z minus? Suppose that if you have a crystal like sodium chloride, uni positive and uni negative ion. So Z plus is equal to 1 for this and Z minus is equal to 1 for this. So for sodium chloride, Z plus into Z minus is equal to what? 1 into 1 is equal to 1, right? Similarly, if you take here magnesium chloride or magnesium oxide, Mg2 plus and O2 minus. So here Z plus is equal to 2 and here Z minus is equal to 2. So Z plus into Z minus is equal to 2 into 2 is equal to 4, right? So and rest are, you can take the rest are constant. So basically the two factors on which this lattice energy depends, so you can say U is directly proportional to Z plus, because E is the charge 1.6 into 10 power minus 19 coulombs, Z plus into Z minus by R, and you can write R is equal to R plus plus R minus in the lattice, right? So lattice energy is a general expression for lattice energy you can give with this equation, and this is a useful equation for you people, because you know if you know the radius of cation and anion and Z plus Z minus, then you can very easily say, okay, because no question you are given to calculate the lattice energy, right, by using this equation, electrostatic equation, right? So but for comparing you can use this, and such questions may be asked. So suppose that if it is given that, okay, if this Mg2 plus for which NaCl and MgO, for which lattice energy is greater or smaller. Suppose that some comparison question is asked, NaCl and MgO. Suppose that it is asked for which the lattice energy is more, right? Okay, now come to this. Na plus Mg2 plus, for which the size is small, obviously Mg2 plus size is small. Cl minus and O2 minus. Okay, Cl minus is little bit larger than O2 minus. So Cl minus is larger little bit, but here Mg2 plus is smaller. So and Na plus is larger. So R plus plus R minus are greater for this NaCl, and Z is also see 1 and here Z is 4. So obviously the lattice energy of MgO is much larger than NaCl. Lattice energy, right? So in this way, this equation will help you to compare the lattice energy. Very useful equation, right? So lattice energy you can determine by using this equation, but don't use this equation for exact quantitative calculation, not included in your syllabus. You just use this form, this general form, to compare the lattice energy, right? For example, suppose that if it is given that LiCl and CSCl, suppose that it is given CSCl. So now it is asked, okay, tell the what is which have greater lattice energy and which has less lattice energy. So Z plus Z minus is same for both. Uni positive, uni negative ions are okay, right? And R plus, see, R minus is same for both chloride. R plus, now you have to decide on the basis of R plus. So R plus is smaller for this LiCl, so lattice energy for this is more than this, right? Order of lattice energy. Lattice energy, right? So in this way you can calculate the, I mean you can compare the lattice energy for different salts, right? For different salts you can compare. So Z is basically what? Number of that ion, positive ion, negative ion, and E is the charge, and uh, sorry, Z is the magnitude of charge present over the cation and anion, right? Okay, now see one more point I have written. So hopefully all of you are clear what is lattice energy. Lattice energy is the amount of energy released in the formation of 1 mole of crystal lattice, or amount of energy required to dissociate 1 mole of crystal lattice. But this is the way how to define. This is the exact way how to define the lattice energy. Now see this lattice energy, you can compute this lattice energy with the help of Born-Haber cycle, that is a thermodynamic cycle, and calculation from Born-Haber cycle and calculation from this equation, right? Equation 2, this equation. Both will give you the comparable result, right? So Born-Haber cycle, a thermodynamic expression for the calculation of lattice energy, lattice enthalpy. See, suppose that we have Na solid. I'm first I'm taking this NAs. Okay, first I will take general expression, then I will show you through the calculation. Suppose that some metal is there, metal solid plus half of x2, this is equal to mx solid. So in the thermodynamics you will study, if any compound is formed, 1 mole of any compound is formed from its elements, not from any other compound. Suppose that you are talking about the carbon dioxide. So carbon dioxide should be formed from carbon and oxygen, not from heating calcium carbonate. So if any compound is formed from its elements, so whatsoever the energy change, that is called delta H formation. So delta H formation, delta HF for this crystal, suppose that this is given minus Y kilojoule per mole, right? And this delta HF is called enthalpy of formation. Enthalpy of formation, right? Now see, and see how to we are achieving this state mx. Now I am explaining this step by step. Suppose that this solid is given to you. When you give energy to this metal, what will happen? What will happen? Is it immediately loses its electron? The answer is no. When you provide heat, first it will convert into the liquid. So I am not converting here in liquid, I am directly converting this into gas. So conversion from solid to gas, whatsoever the energy changes, that is called enthalpy of sublimation. This is called enthalpy of sublimation. Now, after sublimating this, now you have to put more energy. So when energy is absorbed, then it is written positive. So this is positive. See, energy is here released, then it is negative. Now you have to put energy to remove one or more electrons. So I am removing here one electron minus one electron. So whatever energy is involved here, that is delta H ionization energy. So you will get M plus gas, right? M plus gas. Now see here, half X2, first you have to convert this into X gas. So this is called what? Delta H dissociation energy. Dissociation. Since it is given for 1 mole, so you have to take half of this, because half mole of this is. So because this is custom that this delta H dissociation you will get always for 1 mole. So you have to take half mole. This plus this electron, what this electron which metal has loses, this will gain by this X minus. So here energy will release, and you know what is called is electron gain enthalpy. So you will have this X minus gas, right? X minus gas. Now you have M plus gas, X minus gas. So M plus gas and X minus gas, they will combine with each other, and there are different stages in between that. First they will form ion pair, then they will form MX gas. I am ignoring all those steps and I am considering directly that this is converted into this, right? So there is a cycle, that's why it is called Born-Haber cycle. So whatsoever the energy is changing in this step, that is called lattice energy as per the definition. Lattice energy, right? Okay. So see, this is all these whatsoever I have shown here in different steps, 1, 2, 3, 4, 5. All these 5 steps are embedded in this one step. So as per thermodynamics, delta H is a state function, so it is independent of path. Means if you are carrying out any thermodynamic process in one step or in more than one step, the energy change will be equal if initial and final states are same. So from this initial state to this final state, I am going directly from here to here, and I am going indirectly from here to here. The enthalpy is same. So this is called a state function. Suppose that if you are suppose that I will explain you some other by taking some other example. Suppose that this is our initial state. Pressure is P1, volume is V1, temperature is T1, and 1 mole of gas we have taken. 1 mole gas. Here also 1 mole gas, and final pressure is P2, V2, and temperature T2. So we have 2 different paths. Suppose that along this path, suppose that from here to here also 1 mole of gas is there. 1 mole gas is there. Suppose that we are moving from here to here, and temperature is constant here T1, and pressure is I am taking P2, and volume is V dash. Suppose that pressure is P1, pressure now changing P2, volume from V1 to V dash, temperature remains constant. So from here to here, which type of path is this? Isothermal. Isothermal. And from here to here, now pressure is constant P2, volume from V dash to V2 and from T1 to T2. So basically this is isobaric. Isobaric. Right? So whether we are moving in 2 step or we are moving in a same 1 step, directly from here to here, I'm changing pressure from P1 to P2, volume from V1 to V2, and temperature from T1 to T2. So if here enthalpy change is delta H1, and here enthalpy change is delta H2, and here enthalpy change is delta H3. So as per the thermodynamics laws, we can write delta H3 is equal to delta H1 plus delta H2 always. And this is the property of state function. This is the property of state function. They are path independent. They are path independent. I have designed 2 different paths. In one path, some portion we have moved isothermally, and in the next part we have moved isobarically, and here we are continuously changing pressure, volume, temperature, all 3 variables. We have chosen that path. So energy change is always equal if initial state and final state are same. So if any thermodynamic conversion you are doing in 1 step or in more than 1 step, the state functions are always same, independent of path. Right? So this is the, see here, we are moving from M solid half X2 to this is gas, sorry, to Mx solid, and we are moving from here to here, from here to here to here, enthalpy change is same. So as per the law of thermodynamics, we can write here that delta HF is equal to delta H sublimation plus delta H ionization plus half of delta H dissociation and minus of this delta Eg and plus of this lattice energy. Although lattice energy is negative, but if you put this negative here, don't put it, because this you are going to calculate. So if you are going to calculate this, then this value will come negative automatically. So here you can write delta H lattice or lattice energy. So by using this equation, you can very easily calculate the lattice enthalpy for this any given salt. So if you have data of this formation, delta H formation, delta H sublimation, delta H ionization, dissociation, electron gain enthalpy, and this delta H formation, then you can calculate this delta H lattice, right? So let's I write some value and to calculate the delta H lattice for sodium chloride, right? So first I will note down the values, then we will do the problem. Now see, this is the question. Calculate the lattice enthalpy of NaCl for this data is given for this. This is not for NACL. This is for NA, right? So you just use this equation, Born-Haber equation, and simply you can calculate. See, delta H formation of NaCl minus 410.9. So here you have to put minus. So I may write here again. Delta H formation is equal to delta H sublimation plus delta H ionization plus half of delta H dissociation minus delta H EG plus delta H lattice, right? So delta H formation is given this, so it is equal to minus 410.9. Sublimation is given 108.4, 108.4 plus ionization is given 495.4 plus 242, so 1 by 2 into 242 plus, so minus 348.05 plus delta H lattice, right? So when you solve this, so what this will come, this will come 724.7, 724.7, right? So we can write here delta H lattice is equal to minus 410.9 minus 724.7 plus 348.05. So this will give you how much? Minus 787. Minus 787, okay, kilojoules per mole. So it means this amount of energy is released. This amount of energy is released in the formation of 1 mole of sodium chloride lattice. 1 mole means Avogadro's number of ions are there. Means you can say twice of Avogadro's number, because sodium chloride. So Na number of sodium ions and Na number of chloride ions. So this amount of energy is released. So if you want to cleave the 1 mole of crystal lattice, so you have to provide this amount of energy to the system, right? This amount of energy to the system. So if we want to completely dissociate 1 mole of sodium chloride crystal lattice into what? Na plus and Cl minus, right? Then have to put or provide 787 kilojoule energy to the system, to the crystal. Energy to the crystal. This is for 1 mole only, right? So if you have 2 moles, 3 moles, then accordingly you have to provide this amount of energy. Means if you want to, dissolve this sodium chloride lattice in water, you have to put this energy. So means if you are telling that okay, this sodium chloride is soluble in water, means sodium chloride when mixed with water, this amount of energy per mole, it is managed by sodium chloride with water. Means this energy is provided by different physico-chemical processes which are happening between water and sodium chloride. This amount of energy system itself managed. You cannot say that sodium chloride is spontaneously dissolved in water, so without energy this will dissolve. No, it is not like. If anything is happening around us, every process involves energy, right? So spontaneous or self solubility or dissolution of sodium chloride in water doesn't mean that the process is happening without energy. No, not like that. The process must involve minimum this amount of energy to completely dissociate 1 mole of ionic lattice. Means 1 mole of this bond, ionic bond, right? So this amount of energy is managed by system itself. Means there is something happening with ions and water molecule between, so that this amount of energy is released from there, and that energy cyclized to dissociate the lattice of sodium chloride. So this is the reason why, if you want to make some correlation in the solubility of any crystal, so you have to have the knowledge of lattice energy and hydration energy, right? Now one thing is very clear, that if you move down the group, like in the first group or second group, because they will form usually ionic solids, so lattice energy down the group increases, because you know this size, if you see this this equation, size increases. So you can say straightforward that in a group, like in first group or second group, for given type of salt, lattice energy down the group decreases, right? So the lattice energy, what is the periodic trend for lattice energy? The lattice energy for given type of salt, not mix and match, given type of salt, like if you take MCl, so take chloride of all the lithium, sodium, potassium. Don't take chloride of lithium and bromide of sodium and iodide of potassium. So that's why for the given types of salt, right? Given types of salt, from top to bottom, bottom, lattice energy decreases. Lattice energy, right? And from left to right, it is what? Increases. Lattice energy increases. So suppose that sodium chloride and magnesium chloride is given, so the lattice energy of magnesium chloride is much larger than sodium chloride. because both the factor are favored to the magnesium chloride, means size as well as Z both were favoring this magnesium chloride, right? So this is the periodic variation in the lattice energy, right? Now see hydration. What is hydration and hydration energy, right? Hydration of ions and hydration energy. Hydration energy. Right? So how, first see how this is defined. The net heat change in the hydration of in the hydration of 1 mole of 1 mole of ions from gaseous to ions from gaseous to ion from gaseous to aqueous medium, right? From gaseous to aqueous medium, right? So the net heat change in this step, basically this is called hydration enthalpy or hydration energy. Is known as hydration enthalpy. And you know, delta H hydration is always negative. Negative always means exothermic. Right? And you know, delta H hydration is directly proportional to, or you can say uh, 1 by r plus radius of cation plus 1 by r minus, right? So means uh, the hydration enthalpy, in hydration enthalpy we are not treating this ions as a single unit. We are treating ions as an independent unit, because if see in the hydration, see ion in the gaseous and ion in the aqueous, so every ion contributes in the hydration enthalpy independently. But if you see here in the lattice energy, I am taking this R plus and R minus, means sometime what will happen if cation is so small and ion is so large, so lattice enthalpy depends only on the size of larger ion, not the size of smaller ion. That is insignificant. So sometimes it happens, but not the hydration enthalpy. Hydration enthalpy is independently you have to define with respect to cation and with respect to anion, right? So hydration enthalpy independently varies with the size of cation and anion, and it has also inverse relation. How this hydration is taking place in water? Suppose that we have Na plus. So these water molecule, which is a dipole, and this opposite pole of this water will surround this So delta negative, delta negative, delta negative, and delta negative, delta negative, delta negative. This is delta positive, delta positive. This is water molecule. So what will happen? See, there is a, water layer always associated with this. So this is called Na plus aqueous. Na plus aqueous. Basically, if you want, you can see this in a more clear way like this: Na plus and O. This is the representation of, right. Right. So this is called hydration of cation. Dear students, see this R Na plus aqueous, Na plus aqueous is equal to R Na plus gas plus 0.85, right? Approximately this is contributed by water. This 0.85 size is contributed by water. So this is the approximate relation between hydrated ionic radii, right? And but not in all cases you can say this. In some cases two layer of hydration is taking place, like in case of lithium. So this is, I am telling you, the average one layer of water will contribute this 0.85, right? This is the reason why the ion which is largest in size in the gaseous phase, that becomes the smallest size in the aqueous medium, right? In some cases you will find that I have shown here single layer, double layer, triple layer hydration is taking place, right? So this is called hydration. Similarly, chloride ions are also hydrated, but this time water opposite pole will surround this. This is negative, so positive, delta positive, delta positive, delta positive, delta positive, delta positive, 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 and delta negative. Right. So see, in this process, in this hydration process, energy released. In this hydration process, energy released, energy released, energy released. Right. So if, see, here to dissociate 1 mole of crystal lattice, energy absorbs, and here energy release. So for any ionic solid, if delta H hydration is more than delta H lattice, the salt is soluble in water. Soluble in water. So in water, the solubility has this condition. Any ionic solid, if hydration is more than the lattice energy, then that salt is soluble in water. Right? Clear? Okay, good. So this is the criteria for solubility of any salt in water. But again, we have a problem that lattice energy is also decreases down the group. Now, in the group, because size it has inverse relation with the size. So in group lattice energy decreases, hydration energy decreases down the group, delta H hydration decreases down the group. Down the group. So very difficult. It is very difficult to predict what is the trend of solubility in any group. Now I am showing you one data. See, now see, if you see carefully this table, free energy of hydration or delta H hydration, that will decreases down the group. I have taken this first group, lattice energy data. So if we closely examine this, all decreases. Lattice energy of fluorides decreases, chlorides decreases, bromides decreases, iodides also decreases. And now you can see here for fluoride, this maximum delta lattice energy is maximum. Then this chloride is this, bromide is this, iodide is this. So everything is clear because you know the size of M is same, and FClBri size increases, lattice energy decreases. So every trend is okay. Now what about solubility? In case of solubility, what I have given here, the concept that hydration should be greater than lattice. Now how to compare? Suppose that if you are given NaCl and KCl, NaCl to KCl, right? So NaCl and KCl, and you want to determine that which one is more soluble, right? On the basis of the data, which one is more soluble. So see, what is this lattice energy difference when you move from NaCl to KCl? When you move, then what is the lattice energy difference? Now see the difference. So delta of lattice energy, delta of lattice energy, when you are moving from NaCl to KCl, this is equal to, the difference is what, 770 minus 770 plus 703. So we can take this, what, seven and 67 kilojoules per mole, right? So it is better to take KCl to NaCl. So you can KCl to NaCl. So KCl is minus 703 plus 770. So now this is equal to 67. So lattice energy is decreasing 67. The difference when you are moving from NaCl to KCl, this difference is 67. Now come to the hydration enthalpy. So chloride is same, no need to take the chloride, only you can take sodium and potassium. So delta H hydration from potassium to sodium, K plus to Na plus. So this will come minus 330 plus 406. So this is 6 and 7, right? 76 kilojoules per mole. Now tell me, which is more decreasing? So now you can say that when we are moving from sodium chloride to potassium chloride, delta H hydration is more decreased. So if it is more decreased, means solubility decreases. Means you can say that potassium chloride is less soluble than sodium chloride. So when both the parameters are decreasing down the group, so the only way we have left that we can take the difference of successive values, and if difference is more decreased, then the solubility will decrease, because they see hydration more decreases, lattice less decreases, right? So it means since delta H hydration more decreases for potassium chloride, thus KCl is less soluble than NaCl in water, right? So this is the way how to explain the solubility of this chlorides, right? And you know, these chlorides are so exceptional. So I'm giving you the order of the solubility of first group chlorides. Solubility of MCl, and M is equal to first group metal. So if you see here, the solubility of lithium chloride is maximum. After that you will find cesium chloride, and then after cesium chloride you will find rubidium chloride, and then sodium chloride, and then potassium chloride, right? So this is the solubility order, and for bromides and iodides it is okay, no problem. So now this is very exceptional, very exceptional. So all of you should memorize this, no way, right? Now we can make a general statement for group 1. I will give you the one single statement, and that will help you a lot. See, the statement is the solubility of you can make a point note number 1, the solubility of this is a general statement, solubility of group 1 metal salts decreases down the group, right? See, this statement is true for all the salts except fluorides and carbonates. The solubility of fluorides and carbonates increases down the group. The solubility of fluorides and carbonates increases down the group, right? So now this is exceptional, of chloride is exceptional, that I have explained. Now you can arrange all them in the order of their what solubility. Suppose that it is asked what is the order of solubility of this LIF, NAF, KF and RBF and CSF, right? So see, except this is increases down the group, so what will happen? Like this. And one more point I would like to say to all of you, that don't link the solubility with the covalent character or with the ionic character. See, covalent character, ionic character is a different issue. And if you are try to make a link between covalent character and solubility and ionic character and solubility, then you will be in a big trouble. See, in the solubility, I have never taken the name that this is covalent, so this is less soluble, and this is ionic, this is more soluble. No, not like that. So be extra careful, because you know this covalent character and ionic character, that is a state of property of any crystal in the binding state, in the bounded state. But you know, in solubility there are different parameters and different phenomena we are using. See, suppose that covalent character is dominating there, and if when the covalent character will dominate, when there is a large difference in the size of anion and cation, and you know, once the size of anion and cation have large difference, see here, size of cation and anion have large difference. Analyze this formula. So cation, suppose that cation is too small. So if cation is too small, then this will contribute maximum to the hydration energy. And this anion is large, so this will contribute less in the hydration energy, but this cation is contributing largely in the hydration energy. And now come to the lattice energy, where I have written the formula C here. Now cation is very small and anion is large. Anion is large, cation is very small, so lattice energy largely depends on the size of anion, so lattice energy will decrease. And hydration energy, see, hydration energy, this positive, that will increase, that hydration energy will increase. So, and what is the criteria for the solubility? Salt is soluble if hydration energy is more. So it is a thumb rule for this solubility, that if there is a large difference in the size of anion and cation, that salt is largely soluble in water, irrespective of covalent character or ionic character. Got it? Very important point. So never try to link the crystalline solids or ionic solids have solubility of ionic solid have more covalent character, so they are less soluble. Don't explain this, right? Okay, covalent compounds. See, there is a difference in covalent compounds and increased covalent character. See, principally in ionic compounds, where there are ions, principally ions are present. Okay, this is the secondary phenomena of polarization due to which covalent character is increasing. But due to increase in covalent character, you cannot say the molecule is have the atoms, not ions. Molecule still have ions. So be extra careful. So don't try to explain that if covalent character is more, if size difference is more between two ions, then covalent character is more, so covalent character is more, so compound is less soluble. Don't try to explain the solubility on the basis of this. So I have given you a thumb rule that compounds that contain ions widely different in their size, they are less soluble in water, right? Oh sorry, more soluble in water. So this is the thumb rule. And if you have some data like size data, then you can compare this and you will always find the correct result, right? So this is the solubility of first group salts. Now I have written here, you can do the practice and you can make the other like sulfates, like hydroxide. Suppose that hydroxide, what is the solubility of hydroxide? LiOH, NaOH, KOH, RbOH and CSOH. So solubility of group 1 metal salts hydroxide decreases down the group, right, except fluoride and carbonate. So now tell me which have the highest solubility here in hydroxides. Tell. See, so what should be the answer? This is in where this hydroxide is belongs to here in this metal salt or fluoride and carbonates. Now tell me, what should be the answer for this? You know, I have written here metal salts. Hydroxide is not the salt. This is base, or you can say alkali. So this generalization is not applicable here. So you know, this is again this is not the salt. I have written here about the salts. So the order is this. Fluoride order is same as this hydroxide, because you know size of fluoride and hydroxide is almost same. So this is the order of solubility. Solubility order for this, right? Solubility order, right? And you know, if you talk about the group 2 salts, group 2 salt solubility is smaller than the group 1 salts. Although the hydration energy delta H hydration of group 2 is much larger than delta H hydration of group 1. But you know, delta H lattice of group 2 is much larger than delta H lattice of group 1. So group 1 salt solubility, it is what? Less than group 1 salts. And beryllium salts. This is beryllium salts. Beryllium salts are soluble in water. Soluble in water. This is due to hydrolysis. Due to hydrolysis. Right? So suppose that if you take carbonates, so beryllium carbonate maximum, then magnesium carbonate, then calcium carbonate, strontium carbonate, and barium carbonate. This is the order of solubility. Similarly, if you take sulfate, so in case of sulfate also, beryllium sulfate, magnesium sulfate, calcium sulfate, strontium sulfate, and barium sulfate. This is the order of solubility. So beryllium compounds are usually soluble in water, and they are poisonous as well. Beryllium compounds are usually poisonous, right? And what about hydroxides? Suppose that hydroxides were given. So beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So the solubility of hydroxides increases down the order of solubility. Right? So in this way you can explain the solubility of group 1, group 2 metal salts, hydroxides, fluorides, carbonates, sulfates, right? So this is the concept of lattice energy, lattice enthalpy, and hydrogen energy, and their relation to the solubility, right?